Hello, I'm Anjana, Uday.
And I'm Gertjan Lippertz.
And we are PhD students from University of Cologne within the CRC. And we work on what is known as magnetic topological insulator materials.
Today we want to discuss the growth, band structure and electrical properties of these materials.
Yes, so let's start with the growth. On the left you see an illustration of molecular beam epitaxy technique, which we use to grow high quality topological insulator thin films. The growth principle behind MBE is quite simple. It has these pockets with elementally pure materials in it. As you can see, it has vanadium, antimony, bismuth, tellurium and chromium. You heat these pockets up till the material starts to sublimate. You see that the shutters for antimony and tellurium are open, resulting in molecular beams impinging on the substrate. And since the substrate temperature is much lower than these evaporators, the antimony and tellurium atoms arriving at the substrate sticks to the substrate.
You can compare this to water condensing on a cold bathroom window after you've taken a hot shower.
Exactly. And now if you look at the right, you see the AFM image of antimony telluride thin films, and these triangles that you see are indicative of good crystal structure.
This antimony telluride material is quite peculiar and is called a topological insulator. And to better understand what this means, let's have a look at its band structure. So here in black you can see the 3D bulk conduction band and the 3D bulk valence band. And as you see, the material possesses a 3D band gap. This band gap will close at the surface, as shown by the red and blue lines, forming a Dirac cone. This means that the material acts as an insulator in its interior and behaves as a metal on its surface. However, this material, antimony telluride, has a small problem, and that's that the chemical potential, the Fermi level, lies inside the 3D bulk valence band, as shown here by the dashed green line. This means that there are 3D carriers available for transport, which will mask the interesting physics happening at the surface. However, this can be solved by adding a little bit of bismuth. So here you see bismuth telluride, and you see that this material is intrinsically n-type. So by mixing bismuth telluride and antimony telluride, you can tune the Fermi level to the Dirac point.
And now, if you take this bismuth antimony telluride material, grow it very thin, as well as dope it with vanadium, it makes it ferromagnetic, which means that it opens up a gap between the top and bottom surface. However, this gap closes as you go to the edge, leading to the formation of a 1D edge, chiral edge state. Now, for example, for an upward out-of-plane magnetization, this 1D channel runs counterclockwise at the edge of your sample.
Now you can imagine that such a material would have quite peculiar electrical properties, and this is shown on the left. So you see the resistance as a function of temperature, and you see that the longitudinal resistance, the red curve, increases with decreasing temperature, and this is an insulating behavior. However, at 20 Kelvin, the material turns ferromagnetic, and you see that the longitudinal resistance drops to 0. At the same time, you see that the transverse resistance becomes equal to h over e square below 20 Kelvin, and it's this quantization that is the hallmark of this 1D edge transport.